Hello everyone, welcome you all to this video lecture where I demonstrate experiment number 8 in control lab. So this lab is divided into two parts. First one is for system reduction, second is for nonlinear analysis. First one is the system reduction where we look at three commands, one for cascaded form or we use series command for that. Second one is the parallel form, so we use parallel command here, and the last one is the feedback. So here in this lab we normally do implement using Matlab commands. So this is the task. First task you have to perform is to write a code that finds the equivalent transfer function of the following system using Matlab command, that is series, parallel, and feedback. So what I do, firstly I make this as a subsystem. This is another subsystem. Then I use feedback command to solve this block. After that I will take the series of this k again and with the resultant of the feedback. Then I take loss feedback to calculate the transfer function. So let's see how we do it in Matlab. So or if I open the Matlab, in command window I told you that first of all you have to close all, clear all, and seal. So these three commands actually clear the workspace and close the figures and clear all the variables so that you will start your lab. Now first thing is we have to define this operator s that defines the transfer function. Then I will give the controller gain as 10. You can change any number so that it is easy to implement in command window, otherwise it becomes unknown variable. So first of all I define this is a subsystem, that is s1 1 divided by s into s plus 2 and s plus 3. So if I look at the my lab task, so this is my subsystem s1, this is subsystem s2. I will move back to my command window. This is S2. Then I take the feedback to solve this one inside feedback. Then I will do it for series or cascaded for key. Then again take the feedback. So this till this I will complete my task 1. So just I have to run this. So now if I write here the final result, so this is my final transformation. Okay. So this is my system final transfer. Now, similarly for block reduction, I have part B. This is another part B is given. So here again, I make a system here, subsystem. This is another subsystem. Then I solve these two blocks using parallel command because they are in parallel. Then I take a single block. Then I will take the feedback with this one, this block. Then when I solve it, it become a single block. Then I take the series. So this will give me the transfer function. Now see how we do a Matlab command. So I wrote here, this is the second part. Now sys underscore 1 k divided by s square. Then sys is 2 by s. Then I take the parallel to solve the first two blocks. After that, I define S4 subsystem 4 1 divided by s plus 1. Then I take the feedback. So look here, this is s3 and feedback is s4. So if I go back to my, so this is my s4 and the resultant of this one is s3. Now this is in feedback form, so that's why I take the feedback here. Now after that, next step is take the series, so it will give me the result. Now let's see what we get here. If I run these commands, this is the transfer function I will get. So this is the first part of the lab. That is a bit very easy, and I use it using command script file here. Now the second part is about the nonlinear behavior. So effect of nonlinear component on system response. So normally we do linear modeling, but in real time implementation we have nonlinear behaviors built in the system, that is either due to the saturation means that there's a limit of the actuators that give the input, so they are saturated, so they have maximum value, you can't exceed them. If your simulation exceed that saturation value, then this will play a nonlinear behavior in your response. Second one is the dead zone. Dead zone means that when we have a very small input to the system and it didn't response to that input. In that case, we come up with dead zones. And last one is backlash. That is due to gear system. In gear system, we have two components are connected with each other, but they are unable to connect it perfectly. So there always a difference between teeth of the gear. So when one teeth moves, other remains unmoved when it is touch, and similarly, so the difference between two teeth create this backlash. So these are three basic nonlinear behaviors that we normally have in real-time system. So saturation means, for example, I give you another example. If you have a spring and you press the spring, but there is a physical limit when you can't press it further. So these are the reasons when we have. So to analyze these things, we use an example that is available in your book. It is antenna control example where we consider motor and load that you can find in chapter number 2. So this is the velocity of the motor, and this is the angular displacement. So this is the input voltage, and this is the velocity, angular velocity. So this is the transfer function. Now we use this transfer function to evaluate the effect of nonlinear behavior, that is saturation, dead zone, and backlash. Now look here, this is a first order system because it has only one pole, so we easily calculate that time constant is reciprocal of pole location, that is 1 divided 1.71. Now, first task is to study the behavior of saturation of 5 plus minus 5 volt the motor. So this is the simulating diagram where we have to give a step input of 10 volts. Then we introduce a saturation of 5 plus minus 5 volts, and this is the motor dynamics, and we see what happened if we include the saturation. Then again we use the same transfer function without saturation, and we will compare it, and we wrote our observation here. Now for this system, what we do, we have to go to simulink model file. Now here I implement is saturation case where I take the step input because this is 10 volts, so I have to look in the sub block of step. We have to put step time 1, initial value 0, but we have to put 10 as a final value so that we will give the 10 volt input. Now after that I introduce the saturation block, then I have to double click on it. The upper limit I have to change it to 5, lower to minus 5, so that which is the requirement of our task. Now after that I double click here. Here I put the numerator, the value of the numerator that is given in task, then in the denominator as 1 into 1.71. Now then I will introduce a mask, okay, and the scope. Similarly this one. So where I get this saturation and step. So if I go to the library, so sources give you the step input that is available here. You just pick from here. Then sinks give you the scope, okay. Now you have to implement the mask, so you can use it from commonly used mask is there. Now the next thing you require is saturation. So look here, dead zone is available here, backlash is available here, saturation here. So for this task, the three things available in discontinue, continuous block library. So for transfer function, you have to go to the continuous and you pick this transfer function. When you pick it, double click on that and you will get the result. Now in this way I will implement this whole block. Now similarly for next task, Now I run this, I will get the result here. So this is the result which I am getting here. Now I get this result. This is without saturation and this is with saturation. Now similarly for task 2, if I go to lab again, now for task 2 we have to implement the dead zone. So dead zone is between -2 and 2, but here I have to apply the sine wave with amplitude 5 and frequency 1, and also we have to look for angular movement. So in that case we have to use the integral, so that when integrate this thing we get the theta here instead of omega. In first case we have omega. Now what I do here I introduce the integral. Okay, now for dead zone case I introduce integral here in both cases. Now dead zone, for sine wave, if you click it you have to put amplitude 1 and frequency 1 here. So and this means that you are giving this amplitude 1 and frequency 1 input. For dead zone you have to put the dead zone value, that is between -2 and 2, you have to put here, then put OK, then this is the same, then run the system, you will get the result for dead zone. Now this is the result I am getting with the dead zone. So you have to look here what happened. The amplitude is down, also we have a slow response. Now we move to the last task and it about the backlash, that is due to the gear issue. Now for backlash we have to define the band here, that is 0.15. Now for same input here, and what how we do that here, I use the third one is backlash case, and look here I put same input and transfer function, then if I double click it, band is 0.15. Okay, now if I run it I get the result here. Now look here, this is the result I am getting, that because of this backlash we have a delay in the response. This is without backlash and this is with backlash, so there is a delay in the response. Okay, also there are some time where there is no output, we are getting that same. So now the next thing is about the task. If I go back, so this task has, you have to ask, you have to write observation here for all these tasks. So how you do that? Now if you go to your book and on page 196 in chapter 4 with section 4.9, this will explains the effect of nonlinear time response. So this is actually implementing this lab here. This lab is implemented from here. So look here, this is the result you will get without saturation, with saturation, when you implement the lab I told you. Now you will get the analysis is already discussed in these few pages. Just go through it and understand it and then write yourself on the lab report. So this is without dead zone and this is with dead zone. You have to analyze in terms of amplitude, output in terms of time delays and response overall. Okay, so these things are available in this tool here. Okay, so thank you.